All right, we're about to pull back the curtain on one of the most powerful, kind of magical ideas in all of statistics. Seriously, this is the secret sauce that makes everything from election polls to huge medical studies actually work. So let's dive right in.
You've probably wondered this, right? I mean, it seems absolutely impossible. How can you ask just 1,000 people who they're voting for and have any clue what millions of people are going to do? It feels like a trick, but I promise, by the end of this, you'll see it's not magic. It's just really, really cool math.
So here's the basic problem. We want to know something about a massive group of people. Let's call that the population. But we can't talk to every single person. It's just not possible. So what do? We grab a small, manageable chunk of that group, and we call that our sample.
And this is basically the game plan. You have the whole population over here, and it has some true value we want to know, like the actual average height of everyone or the true percentage of people who love pineapple on pizza. We call that the parameter. Since we can't get that, we take our little sample and we measure it. That measurement is called a statistic. The entire goal of this whole thing is to use our known statistic from the sample to make a really good guess about that unknown parameter of the population. Okay, but here's the big question, the one that probably keeps statisticians up at night. What if our sample is, well, weird? What if, just by pure random chance, we pick the only 1,000 people in the country who happen to be unusually tall? How can we be sure that our one little sample isn't totally misleading us?
Well, to answer that, let's try a little thought experiment. Forget about taking just one sample. What if we had a superpower? What if we could take a sample and then another one, and another, hundreds, even thousands of times? What would happen then?
Just picture it, we're reaching into this big population again and again. Each time, we pull out a sample, we calculate its average, and we write that number down. Then we do it all over again. Now, each of those sample averages is going to be a little different, right? Some will be a bit high, some a bit low. They're going to bounce around.
Now, if we took all of those individual sample averages we collected and plotted them on a chart to see how often each value came up, what we would build is something called a sampling distribution. You can think of it like a master map of every possible average our samples could give us and how likely each one is to appear.
I know that sounds a little abstract. So you know what? Let's stop imagining and actually do it. We're going to create our own tiny little universe with just a few numbers so we can see this whole thing happen with our own eyes. And this is it. This is our entire population. Just 5 numbers. That's it. So we know everything about it, right? For example, we can easily calculate the true average or mean of these 5 numbers, and it's 10. Okay? Just lock that number away in your brain. The true mean is 10.
Okay, now for our experiment. We're going to take every single possible sample of 2 numbers from our tiny population. When we do that, we get these 25 possible pairs. And the number in the parentheses next to each pair is just its average. Now, if you look at that grid of averages, it just looks like a random jumble of numbers, right? All over the place, from 6 to 14. But there is a secret order hidden in that chaos.
Because watch what happens when we count up how many times each average appears and plotted on a graph. Suddenly, bam! That random mess organizes itself into this perfectly symmetrical, beautiful bell-shaped curve. Now think about that for a second. Our original population was totally flat. Each number appeared once. But the distribution of its sample averages is anything but flat. This is our first real look at a sampling distribution.
And here comes the first, just totally mind-blowing reveal. What do you think happens if you take the average of all 25 of those sample averages? Well, you do the math, and what do you get? You get 10. Exactly. The same as the true population mean we started with. The center of this new shape we created points like a perfect arrow right back to the true answer we were looking for all along.
That is just incredible. But believe it or not, it gets even better. So what happens if we change the rules a little? What if, instead of taking samples of 2 numbers, we started taking bigger samples, say 3 numbers or 4? Just watch this. Look at what happens to the shape of our sampling distribution as we increase the sample size, which we call n. See, when n is 2, the curve is kind of wide and spread out. When we bump it up to 3, it gets a little narrower. At size 4, it's even taller and skinnier. The bigger our sample, the more tightly all the possible sample averages cluster right around the true mean. This means a bigger sample isn't just a bigger sample, it's a more precise one. It's much less likely to be one of those weird outliers.
So this amazing, predictable pattern, this isn't a fluke.
It's not just some weird quirk of our 5 little numbers. This is one of the most important and fundamental rules in all of statistics. It has a very cool name, the central limit theorem.
And this right here is the heart of it. It says that it doesn't matter what your original population looks like. It could be totally skewed to one side, it could be flat, it could be a lumpy mess. It just doesn't matter. If you take samples that are big enough and you plot their averages, the picture you get, that sampling distribution, will always start to look like that perfect, predictable, normal bell curve.
And this image is the proof. It's so cool. Look at the top row. We've got 4 completely different looking populations. But as we start taking bigger and bigger samples, as we go down the columns from a sample size of 2 to 5 to 30, look what happens. Every single one of them, no matter how weird it started, transforms into that same familiar bell curve. The starting point doesn't matter. The destination is always the same.
Okay, so let's bring this all the way back to reality. What does this amazing piece of theory have to do with those real-world polls and studies? Why is this such a game changer?
Well, it all comes down to this. Thanks to the central limit theorem, we know 2 absolutely crucial things. 1, we know the center of our bell curve is going to be the real answer we're looking for. And 2, we know that the spread of that curve, which has a special name, the standard error, gets smaller and more predictable as our sample gets bigger. Those 2 facts put together give us a superpower.
And that superpower is this. We don't actually have to take thousands of samples in the real world. We only need to take 1. Why? Because the central limit theorem tells us about the shape of the entire universe of all possible samples we could have taken. So we know exactly how our 1 sample fits into that predictable pattern. It's what allows a pollster to take 1 sample of 1,000 people and then say, with 95% confidence, that the true result for the entire country is within, say, plus or minus 3%.
And that's it. That's the secret behind averages. It's not magic at all. It's the beautiful, predictable logic of the central limit theorem. So next time you see a poll in the news or read about a new drug trial, you'll know the secret that makes it all possible. So now that you're in on it, where else in your world do you see the power of this idea at work?